So, good morning everyone. Today we will start with the next topic, Fourier Series Method using window. So, this is basically the FIR filter designing. Okay. So, what are the steps? If you see the first two steps, they are the same. Draw the frequency response. Okay. After that, calculate the impulse response HN. Okay. Then, as we are telling that we will be incorporating a window depending upon the parameters whatever has been given in the question, we will be calculating the window coefficients. Okay, so we have to keep in mind the length of HDN, which is the H desired N, and WN, length of the window, both should be equal. Okay, so from the questions we will find out what is the length of the HN. Okay, and then accordingly we will be calculating the WN also. Okay, then after that, initially what we were doing, we are taking this impulse response values and we are directly going for the Z transform of HN and then the realization. However, since we have calculated the window coefficients, now there is an extra step over here where we will be calculating H dash N, where H dash N means that window modified impulse response coefficients. Okay, so H dash N, it would be given by H of N multiplied by W of N, some simple multiplication, right? And lastly, not lastly, then the next step would be we will be using this H dash N and we will be calculating the Z transform, and after the Z transform is there, we will be realizing the filter. Okay, that is very simple. It is similar to the previous class examples what we have seen, where we have used the Fourier series method without using the window. Okay, herein we will be calculating the HN values, we will be calculating the WN values. Okay, both will be of same length. Okay, and then after that we will be going for the multiplication of the HN and the WN values. So that will give us a modified HN values, which we call it as H dash N. Now using this H dash N, we will be going for the Z transform and the realization of the filter. Okay. Now type of the windows. There are several types of the windows, and if you see, the first one is the rectangular window. It is just like, see, it is a brick-like structure. And we have already discussed previously that when we have any brick-like structure, there would be this Gibbs phenomena across the discontinuities. Okay. However, still, why we teach this? We teach this because it gives you the foundation of how to work with the stuffs, or the how to work with the this filter numericals in a better way. Okay, so for the sake of understanding only we do it. Otherwise, what happens? Whatever the calculation you will be doing under the normal circumstances, there will be no change. Okay, because if you see the amplitude of the WN, it is 1 everywhere. So 1 multiplied by some values, it will be 1 only. So it will not change the values, but this will help you to develop the understanding of the numerical, how to proceed with the other things. Okay. Now another thing over here, if you see, we have a time domain sequence for the WN, which varies from 0 to m minus 1, 0 to m minus 1, right? So this m over here, it is the length of the filter. This is the length of the filter. In various books, you will be finding various numericals or the various notations. In this case, the length of the filter has been given by m. Okay, so this m is equal to L. And when we talk about m minus 1, L minus 1, what is L minus 1? L minus 1 is nothing but the order of the filter. So here we have given m minus 1, that means it is basically capital M. Okay. Now, if you see the shape of the window function, it is having a value of 1 from 0 to m minus 1, that means n. N plus 0, n equals to small n equals to 0, that means another one in this thing, so it will be n plus 1, it will be equals to basically n. Okay, so this m minus 1, it is basically the n, the order of the filter. So 0 to capital N, we will be having values of 1. Okay, then we have Bartlett, which is also regarded as the triangular window. Okay, it raises up to a certain point and after that it decreases, and the equation for this coefficient is this one. So 1 minus 2 modulus of small n minus m minus 1, that means capital N divided by 2. Okay, divided by capital N. So if you rewrite it, it gets 1 minus 2 modulus of n minus, sorry, n by 2 divided by n. Okay, then we have Blackman filter. So the Blackman filter, this equation is a bit wrong, so please take this equation as the correct one. 0.42 minus of 0.5 cos of 2 pi n divided by m minus 1 plus of 0.08 cos of 4 pi n divided by m minus 1. So this m minus 1, these are nothing but again capital N. Okay, so it will give you a something like Gaussian like distribution. It is not exactly Gaussian, but you will be getting uh, a transiently this values are increasing and after that it is slowly decreasing. Okay, so you will be having this Blackman filter. Okay, then we have the Hamming filter or Hamming window. In the Hamming window, the equation is 0.54 minus of 0.46 cos of 2 pi n divided by m minus 1. Okay, then again we have Hanning filter, Hanning window, sorry, Hanning window, it is given by 1 by 2 within bracket 1 minus cos of 2 pi n divided by m minus 1. Okay, then we are having Kaiser window. So Kaiser window, it is basically a what do you call a function derived empirical formula where we can exactly calculate the order of the filter, and based upon the calculation of the order of the filters and all these things, then we find out these coefficients of the Kaiser window. Okay, so for from numerical to numerical, this function it will vary. Okay, so we will be dealing with the Kaiser window separately. Okay, now among the other 5 windows, rectangular window, as I told you, mostly it is used for teaching purposes. Okay, and it has because as I told you that the brick structures, these rectangular windows, they are having a brick structure and they themselves may introduce some noises into the filtering operation. On the other hand, if you look into, we are left with 4 types of windows: Bartlett window, Blackman window, Hamming window, and Hanning window. Among these 4 windows, the Hamming window and the Hanning window, these are the most commonly used windows. Okay, these are the most commonly used windows. Why this is so? This is so because if you see the amplitude responses of these windows, the amplitude responses gradually increase and then they gradually die down. Even in the Blackman window, if you see, the sharpness of the rising of the this window coefficients, they are quite steep. Okay, So there will be an abrupt increase in the amplitude values, and then there is an abrupt decrease in the amplitude value. On the other hand, if you look into the Hamming and the Henning window, there is a gradual increase and there is a gradual decrease. Like the Blackman window, Bartlett window also, if you see, there is a sudden increase and it raises to a top, and from there again it drops down. Okay, and this increasing and decreasing this thing, the roll off or the slope, it is quite high. Okay, so because of these two, because of this reason, since the roll off of this Bartlett and the Blackman windows, they are quite steep. The Hamming window and Henning window, they are mostly preferred. Okay, they are mostly preferred, but it is not like that these are not at all used. They are also used under some special conditions, but for our case we will be mainly focusing on the Hamming and the Henning windows. Now let us look into an example. So we are having the question: design a LPF low pass filter using rectangular window by taking 9 samples of WN and a cutoff of 1.2 radian per second. Okay, now herein, while we will be designing the filter response, so in the previous cases we have taken a value of 1. However, if you see, in this case we have taken the amplitude response of the filter as e to the power minus j omega alpha. Now what is alpha? Alpha is given by, alpha is equal to L minus 1 divided by 2, or in other words n by 2. Okay, alpha is n by 2. So for low pass filter we know that values, they vary in the region of minus of omega c to omega c, and in the other areas it is 0. Okay, so what is the step 2? Step 2, hdn 1 by 2 pi integration of minus pi to pi h d omega e to the power j omega n d omega, right? Now these limits, what are these limits? This would be minus omega c to omega c. So you see, we have changed it. Was this h d omega? H d omega is nothing but we have defined as e to the power minus j omega alpha multiplied by e to the power j omega n d omega, and you, if you simplify that, you will be getting something like this. Okay, now we have got this equation. Over here we are having omega c. If you see omega c, it has already been given. Okay, omega c has already been given. N we know we have to vary. Alpha we have calculated as 4. So we will be putting the values of omega c and the alpha values, and we will be calculating it. Now if you see over here, in our last class we have discussed about the we have discussed that at n equals to 0 we have to apply the L'Hospital's rule, because there will be a condition where we will be getting 0 by 0. Okay, however, since we have modified this equation, if you see over here, now if you see, that comes at the midpoint. Okay, at the midpoint, that means at h equal to 4 we have to apply the L'Hospital's rule. We have to apply the L'Hospital's rule. So what does that mean? What does that signifies? If you remember correctly, in our last class we have discussed that the symmetric value would be in the across the n equals to 0, small n equals to 0, we will be having the symmetric filter coefficients. Now by modifying this filter transfer function, what we have done is that we have shifted these coefficients toward the right hand side. Now this, whatever we were having at n equals to 0, it has shifted to the right hand side, and across that middle point we will be having the filter coefficients. Okay. Now if you see in our previous class, we had to, for the realization of the filter, we had to modify the functions something like this, okay, to get the z transform, so that we get all the values in the terms of delay. Okay. Now since in this case we have done this, so we do not have any value in the left hand side, so we can, whatever the n values you will be getting, or the coefficient values you will be getting, hn values you will be getting, you can directly apply the what you call z transform over there. Okay. So we start with h of 0. Okay. Now by the rule of symmetry we know h of 0 and h of 8, they will be same. So you do the calculation, it will be same. Again, the value of h of 1 and h of 7, it would be same. H of 2 or and h of 6, it would be same. H of 3, h of 5, it would be same. And h of 4, when you put n equals to 4, and again in the denominator you put n equals to 4, you get to 0 by 0 condition again. So that's why we have to apply this L'Hospital's rule, and by applying the L'Hospital's rule we get 0.38. Okay. Now here we know that the length of the filter would be 9 samples. So we have to calculate the Wn values, which will also be having 9 values. And for a rectangular filter, since we are using the rectangular filter, rectangular window, so we will be having a value of 1 in the region of n equals to 0 to L minus 1, that means in this case 8. Okay, 0 to 8 will be having the value of 1. So if you see W0 equals to W1 equals to W2 equals to, and so on to equals to W8, these will be equal to 1. Now what was our next thing? Our next thing was h dash n we should calculate. So W0 coefficient will be multiplied with h0 coefficient. Okay. Then W1 coefficient, it will be multiplied by h1 coefficient. Okay. Then W2, it will be multiplied by h2, and so on. So in this way we will be calculating this thing, and thereafter we will be going for the calculation of the transfer function, right? So it's just simple. So h dash 0 plus h dash 1 into z inverse plus h dash 2 into z to the power minus 2, and so on, right? So you just see we have just put those values, and we get the hz. Okay. Then you can easily realize the filter. Now similarly, if you say we have this equation, we have this numerical where we are having a band pass filter to pass frequencies in the range of 1 to 2 radian per second using Hanning window having length of 5. Okay. Again, equation, if you see, how how to zoom in. It's not clear. देखो you come forward. I can see it. You come forward. सामने आ रहा है. But it will not allow me to use the pen then. No, it's okay. where were we? Yeah. So HD omega, you will be having this thing. So my writing pen will be disabled over here if I zoom it. So you have to bear with me then. So we are having e to the power j omega alpha in this region. Okay. So the region has been clearly defined. Okay. So we will be getting two areas. Okay. Minus omega c2 minus of omega c1, then omega c1 to omega c2. So you just put the values. Now why over here it is omega c2 to omega minus of omega c2 to minus of omega c1? I hope everyone knows. Okay. And why the next one is omega c1 to omega c2? Okay. So after you solve this, you get this equation, right? Now after you get this equation, we have this omega c1 as 1 radian per second, and the second one is omega c2 is 2 radians per second. You just replace the omega c1 and c2 values at these locations. Alpha value we have all we can calculate L minus 1 divided by 2. So this is alpha. So alpha value you will put. Okay. Then we are having this Hanning window. So in the Hanning window, we have to calculate this window values. So herein we are directly going for the calculation Hn equals to Hdn multiplied by Wn, where Wn is 0.5 minus of 0.5 cos of 2 pi n divided by L minus 1. So you just multiply everywhere, just change the value and multiply it. So you will be getting these values, and then after that you just go for the calculation of the exact values. Okay, go for the calculation of the exact values, right? So in this way we will be able to calculate the transfer function of the system. Okay. Now for the Hamming window and Hanning window in the region of this thing, if you see, we are having this equation 0.54 minus of 0.46 cos of 2 pi n divided by L minus 1, and for Blackman window we are having 0.42 minus of 0.5 cos 2 n pi by L minus 1 plus 0.08 cos of 4 n pi by L minus 1 for n equals to 0 to L minus 1. So you need to remember this equation for the Hamming window and the Blackman window. Okay. So any questions up to this point? Then we will be going towards the next method, frequency sampling method. So if you have this frequency sampling method, so over here what you have, design a low pass filter with the following specifications: cutoff frequency 500 Hz, sampling frequency 2000 Hz, and order of the filter it is given as n equals to 10. Okay. Now first what we have to do, we have to normalize the frequency. Normalization, how to do that, I have already told you. Omega c equals to 2 pi fc by fs, fc by fs, so we get pi by 2. So that means this will be our low pass filter, minus of pi by 2 to pi by 2. Okay. Now determine the transfer function. Okay. So hk, where k is denoted by frequency, it is given by 1 in the region of modulus of omega of 0 to pi by 2. So this is 0, Modulus of omega means 0 to pi by 2 में will be having a value of 1, right? So this is what it has been. Now next would be determination of the locations and the amplitude of the samples. So what we are telling herein, the method says it is a frequency sampling method. So we are working in the frequency domain. So this is the frequency response of our filter, and since it is the frequency response of our filter, we have to sample it. We have to sample it. Okay. Now the question which has been given over here, that we have an order of the filter. Order of the filter is 10. So how many samples will be needing? 11. Why? Because length of the filter is n plus 1, which is equal to 11. So what we will do is that we will be, instead of taking the frequency region minus pi to pi, we will be considering it from 0 to 2 pi. Okay. In between we will be having pi, then herein we will be having pi by 2, and somewhere we will be having 3 pi by 2. Okay. Now if you look into the frequency response, it is something like this. Anyone who has not understood this frequency response curve, it is clear. Okay. So we are having this frequency response. Now what we have to do, we have to sample it. Okay. Now how will you sample it? Sampling, as I told you previously, it has to be at definite intervals. Sampling has to be at definite intervals. Okay. Now since the sampling is at definite intervals, so we have to find out the delta. What would be the interval? So that interval, it is given by, that delta, it is given by 2 pi by n plus 1. 2 pi by n plus 1. Okay. Because we are sampling the whole frequency response, and the whole frequency value, it varies from 0 to 2 pi. Hence in the numerator we are having 2 pi, and in the denominator we are having n minus 1, because we need 11 number of samples. Okay. Now if we have found the delta value, now if you want to find out the location, what you will be doing, you have to multiply with the k component, where k will be varying from 0 to n. K will be varying from 0 to n. Okay. 0 to n. So if you see, if I vary the location of k equals to 0 to n, what should be the k delta value? So nothing but whatever this delta value will be getting, multiplied by 0, multiplied by 1. So the delta value, it is basically this 0.57, right? So you can calculate it. 2 pi by n plus 1 is 11. So you calculate it, you will be getting 0.57. You have to put pi equals to 3.14. Okay. So we'll be getting this. Now you have calculated all these things. Now what is pi by 2? Pi by 2 is nothing but 1.57. Okay. What is 3 pi by 2? 3 pi by 2 is 4.71. Okay. And what is 2 pi? 2 pi is nothing but 6.28. Okay. So What is our pass band? Pass band is from 0 to pi by 2. That means 0 to up to 1.57. If it crosses 1.57, we will not take it. Okay. So if you see 0, we will take 1, we will take 1.14. This one we will take. In the next case, it becomes 1.71. It becomes 1.71, which is greater than pi by 2. Which is greater than pi by 2. So we'll be taking the values of k equals to 0, 1, 2. Okay. Next, my next point is 3 pi by 2. It is 4.71. So from that point onwards, I will be taking the value. Okay. So we will again start checking. We will not take this, not this one, not this one, not this one, not this one, not this one. Then when we come at this position, we find this value 5.14. This one also we will take. Next one comes out to be 6.28, but we need the values up to this point. Length of the filter is n plus 1 11. So if you include 0, so up to 10 we will be getting. But why I have calculated this 11, this k for k equal to 11, it is giving me 6.28. So if you remember the z point, the 0 and 2 pi, they are the same point. So just to find out whether my this delta value calculation is correct or not, I have calculated the 11th one. That would give me the 6.28. So but we know 6.28 and 0 are same. So once in the first case we have already taken the 0 value, so we will not take this value. Okay, this is just for your checking whether the delta value what you have calculated, it is okay or not. Okay, now from here, what we do, what we get, capital H of 3, capital H of 4, 5, 6, 7, 8 up to 8 point. From here to here, the values are 0. The values are 0. So what we are left with? We are left with the H cap values, the sampled frequency components we are left with. So how many values we will be getting? 1, 2, 3, 4, 5. So H cap 0 equals to 1, H cap 1 it is equals to e to the power minus j 2 pi by 11 alpha k. Okay, alpha is 5, we have calculated. You just put the value over here and here k is equal to 1. So we get e to the power minus j 2 pi by 11 multiplied by 5 multiplied by, since k is 1, 1. So over here we get e to the power minus j 10 pi by 11. Similarly, we can calculate the other values also. It comes out to be 20 pi by 11, 90 pi by 11, 100 pi by 11. Okay. Now next, find Hn. Okay. So L is equal to 11, which is odd. Herein H of n, it is given by 1 by n plus 1. 1 by n plus 1. Then H cap 0, it should be the only component without the frequency this thing, because this would be the DC component, right? So this will not be associated with any complex component. So H cap 0, it will be alone, plus 2 of real of summation of k equals to 1 to L minus 1 by 2. H cap k you have calculated multiplied by e to the power j 2 pi k n by n plus 1. Okay, by n plus 1. Okay, now this is, again I am writing h of k multiplied by e to the power j 2 pi k n divided by n plus 1. Okay, so You just start putting the values of k equal to 1 to 5, because here we are having L minus 1 by 2, that means 11 minus 1 by 2, that means 5, because we are having this two components multiplied by 2. So we will be putting all these values, we get this equation, which is basically now the Hn. Okay, now once you have got this equation, put the values of n at suitable locations, and you will be getting H0, H1, H2, H3, H4, H5. Then again, since the values are similar, H6, H7, H8, H9, H10. Okay, so from here we need to calculate the this Hz, and then we have to go for the realization of the filter. Okay, so if you have any questions, then we can discuss. This is the whole method for calculating the frequency sampling method, designing of a FIR filter by frequency sampling method. Did you get my point? How to come to this? How we came to this point? How we did the sampling? This is important. Students confuse over here. Again, so this is, see, 0 to 2 pi you are having the values. So you have found out pi by 2 is your cutoff frequency. We have drawn this frequency response. 0 to pi by 2 क्यों आया, you know. Then 3 pi by 2 to 2 pi, why it came, you know, because low pass filter it will be repeating itself, right? So you are having this. So pi by 2 is nothing but 1.57. 3 pi by 2 is 4.71. Our pi is nothing but 3.14, and 2 pi is 6.28. Done. We need to sample it. When you want to sample any signal, whether it is in the frequency domain or in the time domain, you need a delta value. Samples should be equally spaced. You need to calculate the delta value, right? Now what should be this delta value? Our total region is 0 to 2 pi, so maximum is 2 pi divided by how many samples. यहाँ पे order of the filter is 10, but number of samples is 11. So 2 pi by 11 n plus 1 length. Okay, तो वो मिल गया. You got the delta values, but you still don't know the location points. Location को कैसे ये करोगे? If you have the delta value, you have to find out k delta value. So for 0 multiplied by delta when k value is 0. Okay, 1 multiplied by delta, 2 multiplied by delta. How long you will be going? You will be going up to order of the filter n multiplied by delta. So see, up to this thing, up to 10 we have gone, but I told you that I calculated the next point also. Why I calculated the next point? To see whether the n plus 1 जो होगा, this should be equal to 2 pi, that means 6.28. okay, अगर वो नहीं आता है, that means you have done some mistake while calculating the delta value. So वो just for your safety you can calculate. Even if you don't calculate, it's okay. Okay, so you have got these points, right? It is clear up to now. Now the thing is that when you are sampling it, so you have to check the values. कौन कौन सा आप include करोगे? and the values which you will not include. So 0, it is within 0 to pi by 2, we are including this one. 0.57, it is within 0 and 1.57, we should be including it, we will be considering it. Okay, then 1.14, it is within this value, so we will be including this. 1.71, it is in the region of 0, so we will not be including this. Similarly 2.28, not include, not included, not included, not included, not included. Okay, next what we are having, 3 pi by 2, it is 4.71, we have not included 8 because it is before the 4.71 value. So in this range it is having a value of 0. So हमें ये include नहीं करना है. Then next point is 5.14. It would be something over here. We will be including it. So we included that. Then next one is 10th point. It should be somewhere over here. We have included it. Okay. 11th point, if you consider, it is at 2 pi. 2 pi and 0 are same in Z plane. You have already included 0. So there is no question, and already I told you that this is just for your checking purpose. Okay. So यहाँ पे आपको क्या मिल गया? What you got? You got this H cap 0. What is the H cap? H cap का मतलब क्या है? Capping का मतलब it is a sample signal. Okay. So if you are having X of n and if you are having H cap of n, that means X cap n, it is the sampled version of the this thing. So here you are getting H cap k. Okay. So H cap k का value आपको मिल गया k equals to 0, 1, 2, 9 and 10. So if you see H cap value 0, 1, 2, 9 and 10. Okay. So what should be the value? 1 for the H cap 0. Okay, because 0 will be 1, k equals to 0. So basically this is the equation, e to the power minus j 2 pi by minus j 2 pi by n plus 1 multiplied by alpha k. Okay, so when k is equal to 0, you got 1. So you just put the value of k equals to 1. Alpha value we know 10 by 2, 5 आएगा over here. So alpha value is, you just change the value of this k. So you got this H cap values. Okay. Now how to calculate the Hn? You will be designing the filter in the Hn. You have to find out the filter coefficients in the time domain. So for calculating the Hn, it is 1 by n plus 1 H cap 0 plus 2 Re summation of Re matlab we will only take the real components, summation of k equals to 1 to L minus 1 by 2 matlab 5 basically. Okay, H cap e to the power j 2 pi k n divided by n plus 1. Okay, so you change the value of k to this one, expand it. After the expansion you get something like this. Okay, so यहाँ पे देखो we are only left with the n values. So now you just change the values of n and you will be getting this values. Okay, इसके बाद whatever the is the way to do that, you can do that thing. The main thing is you need to understand how to draw the frequency response of the filters. Okay. Anything else? No. Thank you.